Okay, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me introduce our speaker today. It is an honor to host Eric Stoller, who is a professor of mathematics at Virginia Tech, as well as a professor in the Computational Modeling and Data Analytics program. He was head of the mathematics department from August 2018 till August 2022, which was like 2 months ago. Previously, he was a professor of computer science at the University of Illinois at Urbana-Champaign and a senior research scientist at the Interdisciplinary Project Center for Supercomputing at ETH Zurich. He works on the theory and development of iterative methods for large linear and nonlinear problems, including high-performance computing implementations, randomizations, optimizations, inverse problems, and their applications. He is a Leslie Fox Prize winner. His research is highly interdisciplinary, including collaborations on the optimal design of structures and other computational mechanics problems, tomography and image reconstruction, electronic structural computations, photosynthesis, and optimizing plants for carbon fixations and computer graphics. His work has been supported by major grants from NSF, DOE, NASA, AFOSR, and Sandia National Labs. He has served as an editor for multiple journals, among others, for Applied Numerical Mathematics and for SCIAM Journal on Numerical Analysis. And he was the program director of the SCIAM Activity Group on supercomputing from 2003 to 2006. He currently serves on the board of directors of the Computing Research Association. Today, Eric will talk about cheap and robust adaptive reduced order models for nonlinear inversion and design, which is a very interesting topic. So I'm sure you will enjoy his talk today. Now, without further ado, let me pass the baton to Eric by asking one random question. As usual, today's random question, I got that from some random websites. It's, if money were no subject, say you are a billionaire now, what would you do today?
What would I do? I think I would mostly be doing what I would be doing now. So.
Wow. So, okay. So the money doesn't matter. So you will do whatever you're doing right now. That's awesome. You're already a happy person.
Right.
All right. The stage is yours, Eric.
Okay. Well, thank you, Young-Soo, and thank you for inviting me to present here, and thank you for everybody's kind of making time to hear this talk, and I'll be happy to answer questions. All right. So let me first kind of point out a whole bunch of collaborators. So the things I'll be talking about, some of it has been built up over quite a few years, and so two graduate students, Selin Aslan and Drayton Munster, have been done a lot of this work. And then there's several collaborators, Misha Kilmer, Serkan Gugercin, and Chris Beatty, that been very helped me with various components, including the tomography, the model reduction, and so on. The collaborations on especially topology optimization being with Glaucio Polino, who's been a long-term collaborator, and Shelly Zhang. And then some of the stochastic components being worked with Alex Shapiro. And it's being supported by a range of grants. So let me give you a quick overview. So some of the applications of interest are tomography, as well as topology optimization, and more generally PDE-constrained optimization. I highlighted tomography because that's mostly what I'll be talking about. So I'll give a quick idea of the, what the former model is. What's the problem we're solving, and why is it so expensive? I'll kind of take a quick look at the problem in the algebraic sense, because that kind of shows why we can use these same methods for very different problems, which of course for us as computational mathematicians is very interesting. Then I look at parametric model reduction and randomization to solve these problems, these very expensive problems, more efficiently. In this talk, the emphasis will be somewhat on model reduction and then the randomization to help the model reduction, but we've also used randomization more directly to solve these problems. So we look at randomization to efficiently compute reduced order models. So the reduced order models have been very effective, but they're still expensive to compute. And then we look at, because our models are in a high dimensional parametric space, we look at stochastic estimates to estimate the accuracy of the model. And then if it's not good enough, right, we want to update them, we want to do that efficiently. So and then, I'll present some results throughout the talk. And then at the end, I'll have some, discussion, some summary on future work. And so you can kind of see a design from topology optimization that was actually built, using randomization. Okay, why tomography? So this is kind of a quick slide. If you want to look inside the body by only taking measurements on the outside, right, that can be very beneficial to whatever you want to look at or save cost, right? So these are paintings by Rembrandt van Rijn, a famous Dutch painter, and it kind of shows you, what people had to do before we could do tomography. So it's kind of unpleasant for the patient. All right, so in diffuse optical tomography, tissue is illuminated by near infrared frequency modulated light, right? So kind of, you send it in from one side or from both sides, and both happen. The light kind of travels, and then the result is measured in detectors on the other side. So tumors have very different optical properties than the surrounding tissue. That is mostly because they need a lot of vasculature to grow quickly. And so you get a big contrast, and that allows us to recover images of the optical properties of, say, the diffusion field and the absorption field. So dx and ux in this kind of diffusion absorption equation. In this talk, we'll only invert for the absorption u. And this problem is ill-posed, and it's typically underdetermined. It's, in fact, highly data limited. So we'll show that, so per frequency, maybe we take like 1,000 measurements, but you're talking about, hundreds of thousands or millions of cells, right? So it's a highly underdetermined problem. And of course, it's noisy. So we solved the tomography problem in this case. I call it invert for shape, because we're looking for kind of 0-1 type solutions. And for that reason, so that you're looking for things that have a relatively high contrast. So rather than invert for absorption per pixel, which often leads to very smoothed out gray levels because of the regularization, we parameterize the medium and solve for the parameter. So we have a nonlinearly squared problem to solve that kind of looks like this, right? Where MP models, the map from sources to detectors with the medium parameterized by a parameter vector P, and then the observations that are made, and D is the data vector. I put the regularization in brackets because for the parameterization we use, it more or less yields regularized solutions. So we don't need to regularize on top of it. So we'll parameterize D and mu by expansion in compactly supported radial basis functions. I'll show an example in a minute. And then we map that to kind of a piecewise constant function using an approximate Heaviside function. Approximate because we want things to remain differentiable using parametric level sets. And so the modeling I'll talk about in this talk comes from a paper by Agassi, Kilmer, and Miller. But I should say we recently proposed a much better kind of parameterization for these parametric level sets, and you can find this on the archive. And then we solved the corresponding nonlinear squares problem using a specially designed trust region method that kind of regularizes the Gauss-Newton search direction. So it basically regularizes the Jacobian that gives you your stepwise per Newton step least squares problem. And the objective function and Jacobian require a large number of linear solves because there are many sources and many detectors. So just to kind of show you how this looks like, so your expansion in radial basis functions gives essentially like a hilly landscape, which you can kind of, let's see if I can get the pointer going, the laser pointer going. All right, so you have this hilly landscape, and now you pick a cutoff, a level set, and then whatever sticks out above the level set is essentially anomaly, and whatever is below is background, right? So here you can kind of see the colors are not so, maybe not as clear as they could have been. You can see several contour lines, and so it's this contour line here, basically this little blobs here that correspond to the level set, and so that gives you basically this picture. I'm going to give you an example of a reconstruction. So this is our initial condition. We use that initial conditions of this type for almost all our problems, because that kind of, oh, now I need to turn the laser pointer on. Turn on the movie. So the first few steps are very slow, so you can kind of see how from step to optimization things change. They change very drastically in the first few steps, and then they change very smoothly as you converge to the solution. Then at the end, I'll show the original true solution that we've been kind of inverting for. So you can kind of see how the parameter, as the parameters change, kind of the hilly landscape, and therefore the level set kind of changes, and that determines what is considered inside and outside the anomaly. And you can see that you get very, even though the problem is data limited, you get very sharp kind of boundaries, which is the purpose here. Okay, so this is the, it was kind of a friendly anomaly in this case we were inverting. Okay, so here is the forward problem. So you already saw the diffusion equation. So this is basically, this is posted in the frequency domain. So omega here is the frequency modulation of the light, mu is the absorption, D is diffusion. We assume here diffusion is given, and we only invert for absorption. But in general, you would parameterize both and then solve for the parameter. The discretized form, you basically are looking at this transfer function that is parameterized by P. In general, we only have a few frequencies, so they're treated explicitly. We won't do model reduction in frequency space. So the columns of B correspond to the sources. Then if this, is your inverse, the inverse of the discretized PDE, and then C transpose tells you what your detectors see. And the number of sources and detectors can be quite large, from hundreds to, in the order of 1,000. That means, solving a very large number of, in general, 3D discretized PDE. So that makes it very expensive. We want to minimize the misfit, so the residual, which of course is then, your computed outputs minus the data. And so a function evaluation basically requires number of sources times number of frequencies, large 3D PDEs per step. So it's very expensive. For these problems, using a Newton type method is very effective. And so we'd also like to approximate the Jacobian. And so the derivative of A with respect to parameters is relatively easy to compute. So we use kind of a co-state approach or an adjoint approach. So we solve both for kind of the detectors with the transpose of our problem or matrix and for the sources. But so to compute the Jacobian, you need an extra number of detectors times number of frequencies solves as well. So the computational costs are very large. Now a quick look at these problems in the discrete form. So you basically see what you're minimizing here, right? It's like a Frobenius norm of a block bilinear form of a function of a matrix, in this case, the inverse. In the topology optimization case, we would, for example, for compliance minimization, you would be minimizing the trace of this where the columns of F are different load cases, and they could be weighted in terms of which load case you care about more. And so, for example, trace estimates for both of these, right, are very effective at estimating these objective functions, as well as getting derivative. So there is a lot of commonality in the methods you can bring to bear on these problems and other PDE constraint minimization problems. So we're looking at bilinear and quadratic forms involving the linear inverse. More generally, this could be some function of the matrix. And again, that can be done very efficiently with all kinds of Trilov methods. And so the problems we're looking at are tomography optimization, but also with some engineers here looking at certain other quantities of interest using transport of the sensitivity or adjoint equations and so on. So there's a lot of problems where you can bring this technology to bear. For these very expensive problems, we started to use model reduction. I don't know, I think we got some money 2012 or 2013. And so 2015 is our first paper. But of course, a lot of other people have used model reduction, especially for various optimization problems. Not as much, although it's becoming much more for inversion. So at the time, the number of people using it for large-scale inversion wasn't that large. But in things like optimization and so on, and design optimization, there's many, many more people. And, and this is just a subsection. I mean, there's a large number of people involved in this. Our work on randomization got started by some discussions with Eldar Haber and a paper he published with Matthias Chung and some other collaborators. His work by Fred Musta at UCB. We extended this somewhat by combining simultaneous random sources with optimized sources. So that was work that Selin Aslan did as a PhD student, and some other work which I'll talk about here that she worked on was using randomizations for computing reduced order models. So the reduced order models are really used as the venue for solving the problems, but they're still kind of quite expensive. And in that sense, computing the reduced model is still expensive. In that sense, the randomization kind of helped. We also use randomization for these topology optimization or design problems. So that was work with Shelley Zhang, Klaus Cipollino, and Alex Shapiro. A lot of people have worked on estimating bilinear forms more directly. Then one of my other students, or Kasia Sriundowi's work, she did several things, but one of the things was use randomization and recycling to estimate block bilinear forms. This is kind of something we still need to write up and publish, but you can read about it in her thesis. And that last line, I think, is stayed over from another talk. Anyway, so we have these very expensive problems to solve. And so we want to use model reduction to do that. And since we want to optimize over the parameters, we want to use parametric model reduction. So if you saw this, well, so here it is again. So here's the transfer function. It corresponds to an equation in the time domain. So my model reduction colleagues and collaborators like Serkan and Chris like to always kind of go back to the time equation. So we'll describe the dynamics. So we have this highly high dimensional state. So we want to map this to a much lower dimensional state equation. And I'll show in a moment how you pick the state. But let's say you have a trial space VR, which is low dimensional, right? So now you can parameterize X as VR times a small x. And then you choose a test space WR, and you apply a Petrov-Gugercin condition. So basically, you want the residual of this differential equation or dynamical system to be 0. And now you can just multiply through with WR transpose, and you get, in reduced E is WR transpose EVR, reduced A is WR transpose A of P times VR. So the parametric dependency is preserved, and so on. And so now your dynamical system of dimension R, which generally is much, much smaller than N, right, takes the same form. So AR is still parameterized by P, and you have a parameterized transfer function, which is really what we care about here, because this is basically what we measure when we do the tomography. So the whole trick, of course, now is in picking V and W. So how do you pick them? So there's a nice result by Bauer, BT Benner, and Gugercin. So I think this Ulrike Bauer, Chris Beatty, Peter Benner, and Serkan Gugercin. They basically say, like, well, let's let this operator SE minus A of P pull at KSP here. If you pick a set of parameter points in frequency, a pick of sample points in frequency and sample points in parameter space, and you basically solve these systems so that the range of VR, so you typically end it with a rank revealing factorization, because this system tends to be, the columns of this matrix tend to be dependent. But if the range of VR contains the range of the span of all these vectors, and the range of WR contains the range of the span of all these vectors, then you can prove, or that guarantees, that your reduced model or reduced transfer function interpolates a true transfer function at all the SP points that you put into the model. The same holds for the derivative with respect to S and the derivative with respect to P. This, of course, is the one we're mostly interested in if we want to optimize over. And so one of the things that is important to keep in mind here is that it's really about the spaces that you span, not so much the basis that you build, although numerical conditioning, of course, plays. You can think of this as a recipe for building your reduced model. And just to give you some example, so here is one. So the signal comes in from the right and is measured on the left. So here's some model. So these are synthetic problems. This is a reconstruction using the full order model. So we use 36 sources and detectors, 5 interpolation points in parameter space to build the reduced model. And then just the first 5 optimization steps. So that was kind of what we did to kind of get started, but it turns out that it works very well. And we used only one frequency, which is kind of then the 0 frequency. So the I omega over nu term kind of disappears. This gives you 360 basis vectors. If you solve the full problem, it requires 1,100 large systems to solve. In this case, so it's 400 by 400, so about 160K unknowns. And if you use the reduced model, then, okay, it takes 1,260 steps of 250 by 250. So here, we'll basically count large solves. We're kind of implicitly assuming that the large solves are large enough that you use an iterative solver. So we take the number of large-scale solves as a proxy for cost. So here you needed to do, I think, 180, so 5 times 36 for the sources and 180 for the detectors to get 360 basis vectors from the model. So 360 large solves instead of 1,130. So about a factor 4 improvement. Now, for larger 3D problems with more basis functions and so on, this gets more expensive. So we want to still bring the cost of this further down, right? And so now the solution after computing the reduced order model is pretty cheap. So it's really the cost of building the reduced order. So how can we do that, right? So one idea that came up was to use randomization to reduce the global basis cost. And I'll show some how we do that in the next slide. But just to kind of guide your thoughts, right? So the model reduction is very effective, but the global basis is too expensive. And right, so we want to, so you generate, in general, you generate many more vectors than needed. So that is a lot of unnecessary solves. And then you do a rank revealing factorization that may also be quite expensive, reducing the number of basis vectors for the final basis to just a modest number, right? So these are unnecessary costs. And so we know that standard candidate basis is low rank. And so randomization is a good way of getting a good basis for the dominant subspace, so to speak. So we only need a modestly larger number of sample vectors than the rank. And so a lot about that you can find in this paper here. So this reduces solver cost and rank revealing factorization cost. And there's some other things you can update it maybe with Krylov methods if you think your base is not good enough, and there's a variety of things you can do there. And it also helps, with parallelization. So just an example, if you look at the singular values of the candidate basis that you compute in this kind of standard recipe, you can see that you have this rapid decay of the singular values. And so, you really only keep it pretty modest. I think in this case, we maybe kept everything above 10 to the minus 10, but that's already probably more than you really need. But that gives you like 300 something vectors. But so there's a lot you can throw away. And in fact, if we use this randomization and we look at the canonical angles between the computing the basis the standard way and computing with this randomization, you can see that those canonical angles are very, very, so this is the cosines, right? Cosine is close to 1. So the angles are very small. So that tells you you're getting the right basis, right? So normally this would be your candidate basis where each VK corresponds to solving for each frequency for all the source terms. So that's kind of a large number of solves. But then, okay, you stack all of these together, and then you could, of course, hit this with a random vector, but of course, then you've already built the basis. So you're not going to do that. So what we do, so in each element of lambda, here would be drawn, so it would be a Rademacher distribution. So -1, 1 with some well-chosen probability distribution. So we don't want to generate the candidate basis first. So you just write this out in terms of the linear solves. Kind of you multiply your right-hand sides by these random vectors, and then you solve only for those. In this case, we do that kind of, you just take a subset or some sample, b times lambda k, and then solve for this system. It probably is better to do it for this whole system and then kind of combine the multiple solves. We might get away with fewer lambda vectors in that case, but that's not what we've done so far. So why would this work well? So why is this basis, so overcomplete? Well, after a few steps, as you kind of saw, initially you get very drastic changes of the medium, but then they're very, very smooth. And so in this case, we use a finite difference discretization. So the delta A the absorption only happens, kind of shows up on the matrix on the diagonal with very small values. And so small changes in the absorption image suggest kind of low rank and small norm changes to the matrix of these candidate vectors. So in general, you can kind of say that the change in that basis is low rank and small. And so that's why you do this for a set of sample parameter points. You get your vectors look very similar, and so the randomization should be very effective. There's some other interesting components, right? So obviously you can think of these as a random tangential interpolation, but we're still trying to approximate the full model in all directions, right? So it's not clear, but I mean, it's an interesting thing to think about, whether that has some bearing on this problem. And so you can analyze a little bit, like if you look at, say, V1 and V2. So here we just changed the parameter vector. Then, so the change in the matrix is kind of diagonal with a modest number of non-zeros in K. Modest because you say your anomaly changes only a little bit, right? And the only way you change from anomaly to background to anomaly. So this is on the boundary of that kind of change, like a region that moves a little bit, right? You have a modest number of non-zeros that show up on the diagonal. And so you can show that the change in V kind of normalized by the norm of V naught. So that would be the V you compute for the A without any anomalies, is bounded by some constant times H, like your mesh width, and square root of K, where K is the number of non-zeros. Now you shouldn't kind of interpret this as that it goes to 0 for H goes to 0, because K will grow as well. So what you're really looking at is something like the ratio maybe between the area or volume of where you have changes divided by the total volume. But it tends to be a small constant that kind of explains the low rank and small norm changes. So again, here's an example. If you look at the global basis we compute with randomization, and then you look at, say, the A inverse B for various parameter vectors. So here again, I ignored the omega frequency. So for the zero frequency, you can again see that the angles between those spaces. So this is kind of what you miss in subsequent parameter steps. You virtually do not miss anything, right? It changes very slowly. So that kind of tells you this is a good idea. You see that in the Hankel singular values as well. So here's a reconstruction experiment. In this case, this is the true solution. This is the reconstruction using the full order model. This is the reconstruction using the reduced model computed the standard way. And this is the reconstruction using the reduced order model with a few stochastic sources and detectors to do the randomization. You can kind of see that things work pretty well. So here we used 4 sample points and 12 random sample vectors to do this reconstruction. Here's a 3D reconstruction, relatively small problem. I'll show some larger problems later on. And again, you can kind of see this is the true solution. Again, we tend to start with this same initial condition because it works really well. Reconstruction using the full order model, the reconstruction using the reduced order model computed kind of the standard way, and the reduced order model using the randomization. You can basically see you get extremely good reconstruction, even in this much cheaper reduced order model. And okay, here's another one. So here are some kind of results, right? So if you use the full model, so you solve it the standard way, you have about 1900 large solves. The reduced model, if you set it up in the standard way, has only about 500, so about a third to a quarter, and then a lot of small systems to solve, but who cares about solving a 200 by 200 system? And if you use these stochastic sources in the text, you get another factor 3, basically, in reduction from this. So for larger problems, in the 3D case, it gets yet a little bit better, right? So here now we're talking about a factor 15 for the full model. And we see actually later on there's yet more tricks we can do that it gets better and better. But anyway, so it works well and it's cheaper. Now, of course, if we make the reduced model cheaper and cheaper, we still want to know we're doing the right thing. And this is anyway somewhat of a problem with these high-dimensional parametric model reduction. It's difficult to get an error bound. So you can so what we've been doing so far and what we did initially is really use the reduced model blindly. Maybe at the last step, check that your reconstruction is a good reconstruction, but nothing during the minimization. That's because computing a deterministic error bound or is very expensive, right? If you had to do a lot of samples in high dimensional parameter space or kind of do some greedy approach, it would be very expensive. I should say there's kind of an alternative approach. So we're going to use stochastic estimates. There's an interesting alternative approach by Elizabeth Chen and collaborators who use a reduced basis method that does come then with error estimates. But so we figured since we're already using randomization, we can obviously use randomization, in this case, basically, Hutchison trace estimates to estimate the reduced order model. To estimate the objective function. So for example, you could do this with 1 or 2 solves per step. So not 1,000 solves, one for every source or every detector, but just 1 or 2. So that's very cheap. Of course, it's stochastic. So you have to kind of make sure that you have to make sufficiently sure you notice when the reduced model is off. So that's kind of an interesting problem by itself. And well, I'll come back to that. And then the other thing, of course, is if we now notice that the reduced model is not good enough, we have to update the reduced model. Now we're using this inside the trust region method. And so there are these, what they call, I guess, adaptive, or there's another word, trust region method. So if you can show that in a finite number of steps, you can make your objective function sufficiently accurate, then the whole trust region framework still guarantees convergence. And of course, in this case, at least in principle, that's trivial, because if we put an interpolation point wherever our reduced model is kind of failing, then at that step, we would do, the reduced model will do the exact same thing as the full model because it's interpolatory. So then our trust region method will take the same step as if you were using the full model. Of course, we still think that's too expensive. And so if we have to update, we also want a cheap way of updating the reduced model. And so I'll come back to that. So how do we update the reduced order model? So if this is the full model, so this looks something like C transpose, K inverse, where K is SE minus A of P times B, right? And then the reduced model basically looks something like C transpose K times, now you get the reduced model. So that is V times V transpose K, W transpose KV inverse times W transpose. So anyway, you can there's a paper on the archive that lays this out. So you can write this and say, well, how do we bound this? Well, you can bound this by C transpose times K inverse. So this does not depend at all on the reduced model, times an error that looks like identity minus a projection times the right-hand side's B in the Frobenius norm. And of course, the reduced model plays a role here. So T as a function of frequency and parameter looks like this. So it's K SE minus A of P times V times the reduced model inverse times W transpose. And the reduced model inverse again, so that's just W transpose KV inverse. So that makes this a projection. So now assume the reduced order model error is too large at some point P, right? So how could we correct this? Well, if we think of, for now, let's say K times V is QR. So QR is an orthogonal basis for the space of KV. And then your residuals from the kind of reduced model times kind of lifted back into the full space look like I minus T times B. So you can write this in 2 components. It's projection on the range of Q and the orthogonal complement of that. Now, the components in the first part already lie in the space of KV. Solving for those components will give you a contribution in the space V, but that you already have. That's already in your reduced model, so that's kind of unnecessary. So we will only need to solve for these components. And then, okay, we don't want to solve for all of them, so we would like to do as few solves as possible. Well, let's look at the SVD of I minus QQ transpose B, and note that this just involves computing KV and then a projection on the sources. So there's no solves involved, and in principle only a modest number of netvecs. And you can cut some corners there as well. But now let the SVD be given by U sigma Y transpose. So if you now pick the largest singular values and their corresponding left singular vectors, then you could expand V with the K inverse, say U1 up to US. And because then k times that, right, gives you kv, you already have, and the set of vectors u1 to us, which are now orthogonal to v, right, because they come out of this space. And then you can use the singular values to basically set up an error bound to determine how many components you need to pick, right? Because the new basis I minus q tilde transpose times b is bounded by this bound that comes from the singular values, which is bounded by this residual term. So it's kind of residual based combined with an efficient kind of update. And it's very effective. So for one of these 2D examples with 32 sources and detectors, at the point where our stochastic estimate says you need to reject the reduced order model, we have about 11.7% relative error. And just adding 3 additional basis vectors reduces that relative error by another 95%. And so this is basically the error over the different detectors. And so you can kind of see this is the initial error. This is what happens. So it's going down by about an order factor of 10, or from 100 to 5, so 20. So and we didn't solve for 32 sources and 32 detectors. We solved for 3 vectors only, right? So it's quite cheap to do this. And then we do the same thing for 3D problems. So now let us also have a quick look at the importance of that accuracy check. So here the blue line is the reduced order model, and the orange line, or basically the misfit as measured by the reduced order model, and the orange line is the true misfit. And you can kind of see initially they align pretty well, but then at some point the true model doesn't really improve, and the reduced model keep going further. So if you stop here, you could be quite misled by the accuracy that you have achieved. In fact, the accuracy is typically set as slightly larger than the noise level, so it's kind of a discrepancy principle type stopping criteria. And then the green crosses are actually our estimates of the objective function. And we basically say, like, if the estimate of the objective function is some factor larger than the reduced model, then the reduced model needs to be updated. Now, I kind of should say that while this looks pretty bad, in practice, the optimization is quite good. So there is some notion that maybe the derivatives are much better than the function evaluation. So it's kind of interesting. So the reconstructions in this case were still quite good. Anyway, what we do here is so these are the interpolation points. So 3 interpolation points are taken, and here 1 correction is done. So you can kind of see they start to drift apart at some point, not necessarily immediately. Our stochastic estimate tells us that there is too much of a misfit. And then we add an interpolation point, and then you can kind of see the reduced model and the, basically overlaps with the true objective function. And then, of course, the optimization does the right thing. So here we started with 3 interpolation points. But then the thought was like, well, if we can effectively update the reduced order model, maybe we should also do fewer, use fewer parameter points. So build a much cheaper reduced order model, further reducing the cost, but rely on updates during the optimization to kind of fix the reduced model, because it turns out we can do that relatively efficiently, right, with only a few solved. So here we used just 1 interpolation point to set up the reduced model. And of course, 1 interpolation point is just the initial condition, which means that is actually something you can compute in advance. So it becomes a purely offline cost. So it's kind of an interesting thing in terms of the cost evaluation. Of course, they drift apart now much more quickly. And so here at step, 13 or 14, we do a correction, and then they're closed for a while. Here, another correction was done. In this case, the correction may not be necessary because in this case, I need to look at these ones. The estimates also, of course, can overestimate the error, and so you may do an unnecessary update. Well, it's just too bad. But anyway, so you can kind of see we need to do 3 updates, but the reduced model function evaluation and the true function evaluation stay relatively close. So here's a 3D test problem for this case. So this is on a 64 cube mesh. So this is, about 200,000 or 300,000 unknowns. In this case, we have a kind of a grid of 31 by 31 sources and detectors at the top and the bottom, or the left and the right. So we have about 1,000 sources, right? So think about the full function evaluation takes 1,000 solves times the number of frequencies. I think number of frequencies here might just be 1, but still. And then for your Newton step, when you update the Jacobian, there's another 1,000 solves with the transpose. We use 27 of these compactly supported radial basis functions. It gives you 135 parameters. So the parameter space is relatively large. And then in this case, basically to text the reduced model, the noise is quite low. So in general, the noise for these problems should really be order 1%. But this allows us to kind of get better reconstructions. And then basically we can see better how well the reduced model is doing. So here are the reconstructions using the full order model. If we use 3 parameters, sample points and no updates, we also know that you can basically see in the reconstructions, you don't actually see too many differences, which is kind of, like I said, is an interesting thing that even though the reduced model itself is off, it seems to drive the optimization still in a very good direction. And these are these residual updates with only 1 sample point, which is very, very cheap, and it works still very well. Some costs. Now, since everything is now stochastic, we did a fair, I forget how many, but maybe we did this like 100 times and then looked at the median cost of the solves. And then here are also percentiles of the number of iterations. So the full order model took 23,000 large linear solves. And if you didn't do the first step, because let's say you consider computing that for the initial guess already, right, it goes down a little bit. 3 interpolation points goes down to about 5,000. If you think about only the additional ones that need to be computed, it's only about 3,000. So we're already getting huge improvements. The 1 point, so only the initial guess, if you count that initial guess, right, you're doing about, a factor 10 better. But if you actually take into account that you could compute that reduced model offline in this case and just do updates, then on average, right, you go from 63 functions, a large linear solves to versus 23,000. So you have an enormous improvement in the cost. Of course, the improvement versus doing the reduced model the standard way is not as large, right? But still about a factor 100. So very impressive improvements. All right, so some conclusions and future work. So model reduction is very effective for this problem. And we can reduce the cost of this global basis computation further by randomization, by doing it very cheap and relying more on the updates during the optimization, because it turns out that we can do those quite efficiently. And there's some further things we could look at using the angles between the spaces that kind of are generated. So this is kind of an idea that still has to be applied. The stochastic test is cheap and it allows updating the ROM. Of course, now we did the stochastic test. In this case, was done just by 1 solve. Of course, you can ask if that is always accurate enough. And so one of the things we're very interested in, so this is kind of future work, is how many estimates would be necessary, and you can use a posteriori evaluations to get delta probabilistically accurate estimates for the gradient of the objective functions, because that would allow us to develop a trust region method. So there's some work, this would be slightly different, but there's some work by Chen, Niccoli, and some other people in using stochastic trust region methods that would converge with high probability. So that, of course, is really what you want. And this should be, at an extra cost because you need to do some more samples. So that's kind of something we're kind of working on, and you can find the first attempt at that in Drayton Munster's thesis. There's several more possibilities for efficient approaches. Basically, getting a small ROM, but maybe a little bit better than just based on the initial guess. And then the other thing is, many problems have this similar algebraic structure, and so we want to apply these ideas to a lot of different problems as well. And that's it. Thank you.
Well, thank you so much for the wonderful talk, Eric. It was very interesting and very informative. Thank you so much. Let's have a Q&A session. If you have any questions, you're welcome to unmute yourself and ask questions, or you can put your question on the chat room so that I can facilitate later. So I don't see any questions in the chat. So let me start with a question. Very good, Eric. If you go back to the previous slide where you show the summary or the conclusion.
Right.
So, stochastic test, one of the bullet points is the third one, the major bullet point. Stochastic test is cheap and allows updating ROM. And have you done the performance comparison between, the usual way of updating the ROM and also, the stochastic way of updating the ROM? Those, which one is faster, and any numerical performance comparison have you done?
Well, so the standard way of updating the ROM in this interpolatory mod would basically be kind of the cost of one full function evaluation, right? So they would be solving for all sources and detectors. And then you add those all those directions to your model reduction basis, and we do a rank revealing factorization. So so the randomization would reduce that number of solves kind of drastically, so that you can kind of see some examples. So this would be kind of the same type of reduction of cost as for building the initial reduced model. So I had some numbers here.
Yeah, one requires a full linear solve and the other one does not.
Right.
So it was kind
So
of
that's
obvious.
right.
It was kind of
So
obvious.
that's and then the stochastic estimate in this, at this point, we just do one large scale solve. So it's basically do a trace estimate for do a Hutchison trace estimator for this matrix.
Right.
So that requires one solve. Or do we do two? Do we do it from the left side as well? Okay, I have to. So one or two solves. I think just one. And so
Okay.
again, that's very cheap. But of course, it's not. You can look at these where we do the correction. That those estimates are not always that good, right? So you can kind of see here, for example, while the difference is small, but the estimate for the different, is quite off. So these estimates are not that good. And so here we just went for efficiency. So we just do one solve. In practice, you would probably do a few more.
Right.
And that's where kind of, and so if we apply kind of this theory that I outlined for these, probabilistically accurate, you actually need quite a few solves, and then it gets a lot less good. But we think at the same time, like maybe this, like if you use this is to some degree based on like concentration inequalities, and those are very pessimistic, right? So it may tell you, oh, you need to really do 10 or 12 solves to for these trace estimators to get enough accuracy, but in practice that is overkill. So the interesting question is to strike a balance there. So one is probably less than you would do, but it works, at least for all our problems, right? It did find when they drifted apart, it did notice that. But yeah, so coming up with both stochastically speaking, a robust method that guarantees convergence with high probability, but is as efficient as this, that's kind of a that's an interesting new thing to work on.
Right. All right, sounds good. I don't know if I'm allowed. My next question is, you kind of took a balanced truncations types of reduced model here, and your governing equation is linear. I see, and there are many other types of the reduced model, like such as projection based. I mean, the POD based reduced model. And also, there are quite a work on extending this reduced model from linear to nonlinear problems as well. So, how do you, envision, extending this, framework to the reduced model, which is available for the nonlinear problems, and also further, extending that to the nonlinear inversion problem, or the topology optimization or design optimization, or in
Yeah, I
general,
think for
PDE.
So here we use interpolatory model reduction, which of course is very good because we're doing parametric inversion. So like I said, it has this nice advantage that if at some point the model is not accurate enough, then you add an interpolation point at that parameter, your reduced model at that point will give you the exact same step as the full model would.
Right.
So in that sense, this is kind of very nice. Now, for topology optimization, there isn't like a similar kind of interpretation of an underlying dynamical system. You're not looking at a transfer function. So I think POD there would be the more obvious way to do the reduced model. I think that's kind of what you have done.
Right.
So here, POD. So it's kind of important that, of course, you're modeling the map from sources to detectors, but as a nonlinear function of the parameters. Right? So the PDE is linear, but the map from parameters to the kind of the output of the P, that is not linear. So
correct. Yeah.
So it's a good question how other reduced models would do and how you would bring in the parametric dependence, right? So yeah, I guess if we would do POD, we probably would again take some number of parameter sample points, then solve maybe for some number of source detector maps, kind of add that to the basis. How that would compare? Yeah, we haven't tried to some degree because it looks like the interpolatory model reduction works very well for this problem. But like you said, for other problems, yeah, that's a different question. If we would do this for nonlinear problems, so nonlinear PDEs, then you would probably do something like DIME or empirical interpolation methods to kind of do that. We've done some experiments. In fact, you saw Saifon Chaturantavud's name kind of in the list. So she worked on that. This is some time ago. It was difficult to get it to work really well for some nonlinear. So yeah, so my real honest answer would be, I don't know. If you had a nonlinear PDE, probably depends on how nonlinear the PDE is, how well it would work or not.
Yeah. Sounds good. Okay. Thank you, Eric. Is there any other questions from audience? I guess we have a shy group today. All right. Well, if not, then okay. So if not, let's thank our speaker today. Thank you so much, Eric, for the wonderful talk. It was very informal and instructive, and I enjoyed it a lot. So thank you so much. And starting from today, I hope you will have more collaborations from Lawrence Livermore side as well. That would be the ultimate intention of this seminar series. So all right, thank you, Eric.
Yeah, well, thank you everybody who followed the talk. It was my pleasure, and yeah, I definitely think we'll talk more, Young-Soo, about some collaborations because we have great overlap of interests here. So.
Yeah, of course. Yeah, I will send a separate email to you. Well, let me stop the recording.